Electrostatic effects are common in everyday life. Sometimes they're a help, sometimes a hindrance. This highly charged, thin plastic film is attracted towards other surfaces by electrostatic forces and provides a good seal. Other aspects of the subject are less welcome. People who work in offices often find that they build up electrostatic charge as they walk across the carpet. So when they touch some earthed metal, they get a shock. This is more likely to happen when the air is relatively dry. One of the most dramatic displays of electrostatic energy is lightning, where many thousands of joules of energy are lost in ionizing the atmosphere, ripping it apart. This dust collector experiment shows that even much smaller sparks can put people and plant at risk throughout the chemical and process industries. Every year, these industries suffer many fires and explosions. There's one dangerous incident each week in the United Kingdom that's caused by electrostatic sparks. If we take all of Europe, these incidents occur daily. Often, solvent vapors are involved, but sometimes it's dust that explodes. Fires and explosions can be started in all sorts of ways. Mechanical sparks, electrical sparks, hot surfaces, welding, and many others. Precautions must always be taken to guard against ignition sources, and electrostatic sparks are no exception. If you don't take precautions, this is what can happen. We're going to show you how to assess the electrostatic hazards in a chemical plant. There are 5 questions you have to answer. Could there be a flammable atmosphere? The flammable atmospheres we're talking about are gases, vapors, and airborne dusts. When you're handling liquids, you can normally look up the flammability of their vapor. If they aren't flammable, there's no problem. But if they are, in other words, they've got a low flash point, you do need to assess the electrostatic hazards. With powders, it's not so straightforward, and you need to have tests carried out to determine their flammability. In this dust explosion laboratory, a small sample of aspirin, half a gram, is being tested. We raise the aspirin dust and try to ignite it. If you were using this powder, you'd need to assess the electrostatic hazards. That's the first question on the list. The second one is, can charge be generated? Whenever two materials separate, electrostatic charge can be generated. With uncharged materials, the touching and separating can produce surfaces which are oppositely charged. The effect is greater if the movement is rapidly repeated, with pressure or sliding contact. Electrostatic charging can also happen with low conductivity liquids like toluene, xylene, hexane, heptane, carbon disulfide, and many others. Charge generation takes place where the liquid molecules are in contact with the pipe wall. This can produce charge in the liquid. The faster the liquid flows, the more it charges. It'll become even more charged if it flows through a fine filter, or if there are two liquids that don't mix flowing in the same pipe. For example, water droplets in toluene. Even with a liquid that's a good conductor of electricity, charge can be generated when it splashes or if it's sprayed through a nozzle. The individual droplets carry charge at their surfaces. So what does this mean in practice? In the chemical and process industries, there are many ways that charge can be generated. When you're walking along, charge can be generated each time your shoes touch the floor. You could easily become charged to several thousand volts and not even realize it. The effect is much greater when the relative humidity is low. If you wear insulating shoes, you could become electrostatically charged just by working close to a charged insulator. In this case, the polypropylene bag, which contains a charged powder. This milling operation generates charge because of the high-speed contact of the powder and the mill. But you'd never know the powder was charged just by looking at it. When powder collides with the pipe walls of pneumatic conveying lines, charge is produced on the pipe and the powder. Transferring xylene through this pipeline and filter creates electrostatic charge on both the filter element and the liquid. In splash filling operations, highly charged droplets are produced above the liquid in the reactor. And in this centrifuge, drawing the filtrate through the cake and filter bag generates charge on the cake, the solvent, and the filter. To recap then, electrostatic charge is generated in all sorts of ways, but in itself, this doesn't create a hazard. The next question is, can charge accumulate? Charge has to accumulate on people, plant or product before there can be a risk of electrostatic sparking. Whenever charge is generated, it's being lost at the same time, usually by conduction. In this particular milling operation, charge is generated on the powder and on the metal components of the mill. Charge accumulates on the powder because it has a high resistivity and is lost from the mill because it is earthed. An unearthed mill will accumulate charge. Toluene has a low electrical conductivity and can accumulate charge. Charge is lost from the pipeline because it is earthed. An unearthed pipe will accumulate charge. Powder can become charged as a result of fluid bed drying operations. We can measure the charge with an electric field meter. Laboratory tests on both powders and liquids to measure electrical resistivity and charge decay time can be used to show how much they store electrostatic charge. The powder that came out of the fluid bed dryer is now being tested under controlled environmental conditions to measure its charge decay time. The electric field meter is connected to a chart recorder. As the trace shows, the powder is slowly losing its charge by conduction. This powder will lose all its charge in a few minutes. But powders of high resistivity can retain electrostatic charge for days or even weeks. Even when electrostatic charge is generated and accumulates, it will not necessarily lead to an electrostatic hazard. The next question, could there be a spark risk? To cause a hazard, charge must build up until the electric field reaches the breakdown strength of air. This produces a spark. As we've seen, when this man walks across an insulating floor, charge accumulates on his body. The voltmeter shows that he's stored a potential of over 10,000 volts. The reading falls to 0 when the charge is lost in a spark to earth. The powder pouring out of this blender is of high resistivity. It's also highly charged, so charge accumulates both on the powder and the plastic drum. The electric field meter shows a high reading on the surface of the powder. An earthed probe draws sparks from the drum. Even though you can't see them, they do show up on the oscilloscope screen. Charge can also accumulate if the same powder is collected in a polythene-lined fiberboard drum. Even though the earth clip prevents charge accumulating on the drum, the powder is still highly charged, and the liner impedes the flow of charge to earth, so there could be a spark risk. Whenever there could be a spark risk, you need to ask the final question. Could the spark have enough energy to ignite the flammable atmosphere? Each flammable atmosphere has a minimum ignition energy. This is methanol. If the electrostatic spark has more energy than the minimum for ignition, then there is a risk of fire. Many common solvents have minimum ignition energies that are so low you can hardly see the spark that ignites their vapors. Dust clouds are harder to ignite and have a very wide range of ignition energies. The measurement of minimum ignition energy is an important part of any electrostatic hazard assessment. Sparks occur when unearthed plant becomes charged. So this buggy charges up when it's filled with powder, because its nylon wheels prevent the charge leaking to earth. In this experiment, we have connected the buggy to a spark gap above a tray of acetone. As the buggy becomes charged, a spark is produced. If you wear insulating shoes, the charge you generate in walking can build up. Then, if you walked up to a tray of toluene, the spark you produce could be enough to ignite the vapor. Nearly all flammable solvent vapors can be set alight by this type of spark. Worse still, spark discharges can ignite dust like the fine paracetamol in this tube. A different type of spark, called a brush discharge, can be produced from charged plastics like this drum liner. Although of lower energy, they are still able to ignite gas or solvent vapors. Only powders with very low ignition energies are at risk. So, to assess the electrostatic hazard with a process, you need to ask 5 questions. First, could there be a flammable atmosphere? If so, can charge be generated? If it is, can charge accumulate? If it can, could there be a spark risk? If there is, could the spark have enough energy to ignite the flammable atmosphere? If the answer to all 5 questions is yes, even if it's unlikely, then there is a risk of fire or explosion, and you have to take action to control the electrostatic hazard. Electrostatic sparks are just one of many possible ignition sources that can arise on plant. Controlling ignition sources isn't usually enough on its own to ensure safe operation. You normally use other techniques to prevent fire and explosion, such as inert gas blanketing, which is used for this process. But if a flammable atmosphere could occur at any time, the electrostatic ignition risk does need to be assessed and eliminated. There are 4 areas that need attention: plant, people, liquids, and powders. Earthing plant is always the first essential step in protecting against the build-up of electrostatic charge. The bonding together and earthing of fixed metal installations is a good starting point. Each tank in this tank farm has an earthing point. There's a robust earth connection point and cable on this chemical reaction vessel. The fluid bed dryer is earthed, including its basket. This pneumatic transfer line is made of metal. It's well earthed along its length by the couplings and by bonding the wire inside this flexible connector to the pipe at both ends. Once an earthing system has been installed and checked, it still needs regular and thorough maintenance to ensure continued safety. The electrician is using an intrinsically safe ohm meter to ensure that this chemical reaction vessel has less than 10 ohms resistant to earth. You can easily create sparks if you become charged or cause other equipment, such as drums or scoops, to become isolated from earth. Everyone who's likely to come in contact with flammable atmospheres should wear anti-static shoes. You can test your shoes with special equipment, which measures your resistance to earth. In some cases, the correct footwear isn't enough. The floor in this part of the plant has high resistivity, and you could stay charged to a dangerous level even if you were wearing anti-static shoes. When you step onto a conducting floor, you quickly lose the charge and can work safely. Remember, failing to earth yourself can lead to this. Adding powder directly to a reactor that contains a flammable vapor can be dangerous, as it's very difficult to eliminate all